Okay, so I'm Parvez, as you already know, I'm from the University of Edinburgh, and today I'm going to speak to you about shapes. In the natural world, there is a plethora of different organisms that use shape and structure to complement function. There are, this is true, and this is true at every conceivable length scale, I'd say. So at the gargantuan length scale, for example, pterosaurs would use, the fins placed at the front of their cranial structures to enable tight turns mid-air. Whereas typically fins on rockets and planes, they're put at the back to stabilize flight, but of course they can't turn as quickly when the fin is further at the back. So pterosaurs got over that, and they circumvented that problem by having their fins at the front, right on the top of their heads. At the macro length scale, a good example is in trabecular bone, which is a crisscross structured bone, and it's very airy, it's very porous. And that means it's very lightweight, but at the same time, that crisscross structure enables rigidity. And one good example from trabecular bone is the Eiffel Tower, which was actually modeled on the crisscross architecture of this bone. At the nano to micro length scale, you have gecko's feet. And geckos, basically, you've probably seen them running up walls, upside down on ceilings, and so forth. And how they manage to do this is they basically have tubular shaped hairs, millions of tubular shaped hairs under their feet. And on the ends of those hairs, they have spoon shaped hairs. So you've got lots of spoon shaped and tubular shaped hairs, which basically massively increases the surface area of contact that the gecko can have with the surface. And that increases the secondary interactions between the foot and the surface, like van der Waals interaction and so forth. And basically that's how the gecko sticks. And at the molecular length scale, a nice example is a structural example of silk, dragline silks and tubular-form silks, which form the egg cases of spiders. They tend to have a lot of stiff nanocrystals embedded within an amorphous matrix. And these are all proteins. So the stiff proteins are basically linear backboned proteins, whereas the amorphous proteins are like coiled. And a nice analog in the real world would be steel bars. Steel bars, if they're just straight, they're very stiff. You try to pull a steel bar, you won't get very far. But if you turn that steel bar into a spring, the same steel bar, you turn it into a spring, all of a sudden it's compliant. If you take the stiff rods and the compliant springs, you put them together, you get the best of both worlds, and that's how you massively increase mechanical energy absorption. So now I'm going to focus on shapes and how speed can be affected by shapes. There are lots of different examples in nature, but I'm going to focus on one archetypal apex predator, which is the shark. So the shark actually, it's covered in placoids, and they're very fast underwater. And these placoids are the reason for their speed. Now, let me tell you something quickly about the placoids. A fun fact, so to speak, is that these placoids are essentially teeth. So if you ever get the chance to stroke a shark, which probably is quite comforting to a shark, you're actually stroking a huge array of teeth. What's interesting, they're modified teeth. What's interesting about these modified teeth is that they have these micro channels. And I don't know if you can see my arrow. Do you see an arrow moving on the screen? Brilliant. So they have these micro channels here, and these basically work in this way. If you take a plate of glass and you pull it through water, you can just put that glass through water and you pull, and you'll find that it's actually quite difficult to pull a plate of glass through water. And the reason for that is that you have a very fast rate of water movement at the interface with the glass, but then as you traverse further away from the surface of the glass, the water eventually becomes, let's just say for the sake of argument, zero velocity. So as a consequence of this, you'll have a vortex forming. And if you've got a big flat plate of glass, you'll have a very big vortex. And that big vortex will impose pressures, which are normal to the surface, against the glass, and that creates drag. With a shark, you've got lots of these microchannels, and these microchannels basically create lots and lots of small vortices, i.e. eddies. And eddies, they're like these tiny little vortices, which would be more like me tapping the side of a shark with my fingers, rather than having a big vortex that's like, you know, punching hard against the side of the shark or pushing against it. So drag reduction is a consequence of the placoid scales. And this is something that is important to mimic, and this was understood a long time ago because swimming suits have used these more simplified structures in mimicry of the shark skins. And, you know, another fun fact, I suppose, is that in the 2012 Olympics, the shark skin swimsuits were banned because people were breaking too many records. Now, if you look at the structures of that last image that came up, they're actually quite different from the placoids, but they enable the same effect, which is the micro vortices or micro eddies. And this leads us on to a very important point, is how do we manufacture something like a shark skin or a placoid? Because biology is far, you know, the natural world is far superior when it comes to manufacturing things than we are. So the best we can do is come up with these elongated structures for it to be something that's feasible. And this takes us into the philosophy of biomanufacturing, is that we need to think when we're looking at these structures, how can we get the desired effect without getting too complex? It's not an easy thing to do. So you have to think philosophically like an artist in one sense. If you have the sky, you might look at the sky, but an artist looks at the sky and they are able to discretize this into smaller parts. They split it up into lots and lots of pieces, and they can identify then more easily the different colors that actually exist in the sky. And by doing that, they're able to mimic, in effect, the sky. As an engineering designer, we do the same thing when it comes to shapes. We ought to do the same thing when it comes to shape, because by breaking down complex shapes into primitive shapes, we have a better chance of understanding and you know, mimicking through manufacturing processes that exist complex structures to get a desirable effect. I'm going to move on to color. This is a short talk, admittedly, but it's, you know, hopefully it's interesting enough, nevertheless. And when it comes to color and shape, well, I'm just going to give you three examples, three different organisms here. One on the left there is the cobalt blue tarantula. In the middle, you have peacock feathers, which have these beautiful eyes on them. And you'll see the eyes also on the right there in Junonia butterflies. And these are all examples of structural color. That is color that is a function of shape. When it comes to the cobalt blue tarantula, that lovely blue coloration is essentially a function of the flowery shaped cross-section of the hairs that it has. When it comes to the peacocks, you see there's brown and there's green in the eyes, and they can basically alter the coloration from brown to green by increasing the spacing distance between these systematic packings of what I'll call right now blobs. So by altering the spacing distance between the blobs, they can change the color from green to brown to bluish and so forth. And when it comes to Junonia butterflies, they use these very complex diffraction gratings to control coloration. Now, how does structural coloration differ from pigmentation and so forth? Well, basically, normal colors, as pigments, the way they work is that they will absorb and reflect. So the light that is absorbed into a pigment is the light you don't see the visible spectrum, but then if something from that visible spectrum is reflected, that's what you see. So if the red wavelength is reflected, then that's what you'll see. When it comes to structural color, it is a function of angle, and you'll get what is known as constructive interference occurring. Essentially. And when that happens, if you look at, a particular structure at a particular, let's say 75 degrees, you might see green, whereas if you look at it from 15 degrees, you might see purple or blue or something like that. So it is ultimately dependent on the angle at which you're looking at it. And how does this affect things like the tarantula? Well, they can change the shapes of their hairs to also change, therefore, the colors that we see. So basically, if they can have like fairly non-flowery structures that just have refractive indices, and they will appear one color. But then as soon as you start putting these flowery patterns on the surfaces, you'll get blues and deeper blues, more iridescence, less iridescence, ultraviolets, and so forth. So basically, I'm going to stop there and open the floor to questions. You can, of course, when you look at these cross sections, once again, take into account and think about the manufacturing philosophies that are involved when it comes to mimicking these kinds of things. So yeah, I mean, we're getting further and further every day when it comes to biomimicry, but there's still a long way to go.
Parvez, that was very interesting. Can you unshare your screen and then we can
unshare maybe if you leave it shared, because I think there is something that it's actually not correct in what you have reported. Sorry, but I know well the work because it's one of my PhD students that did it when he went to Halted on slide 12. So what you said, it's not partially correct. Say like, actually structural color. So first of all, so you have a diffraction mechanism, and that's true. It's like an interference mechanism. But then you have hierarchical architecture, like you also have in nature. It's always hierarchical architecture. And the color doesn't depend on the shape. The color doesn't depend on the shape. It depends on the smaller nanostructure that you refer as blob in the feathers of the peacock. You actually also have that are inclusion of melanin. You also have this nanostructured on the tarantula, and that's what determines the color. And then you have, I think it's important to say that what is important to say, because one of the people, I know.
Yeah, and what you're saying is true, but of course, I tried to condense things into a 7-minute presentation.
No, I know, but then I think
we can speak for hours about this kind of stuff.
No, Parvez, I just want to say
if you're
something
speaking about something in
important.
7 minutes, you can't usually cover everything.
I understand, but I want to say something that is important.
I totally agree.
I think it's
hierarchy is very important. Not just
if you let me talk,
optics,
I would like to say something that I think it's important.
But of course, not just with optics, but also when it comes to mechanical properties. Without the hierarchy.
So sorry, can I say something?
When it comes to
guys, stop.
Yeah, sorry.
Stop. We know both of you are absolutely amazing, right? So let's
no, but just one thing. I think it's important because this is a misconception. But let me finish, please. Let me finish. So a misconception that many people, when they think about structural color, you always have these things that the structural color change in function of the angle. And this is one of the problem that we found also problematic when we want to work in industry with structurally colored material, because this is a misconception that it's always there. In fact, it's actually not true. There exist multiple different types when you can make a structural color that are angular independent. And this is an example if you use a hierarchical structure, but you can also use a periodic system. And I think this is, especially when you talk about biomimetic, I think it's always important to say that you can actually achieve a huge variety of effect in nature. And that's actually what you want to show, because that's what, in my opinion, it's really important. So apart this clarification, I had a question, which is, what actually do you want to do with this type of architecture? Are you trying to make them? Are you trying to mimic the tarantula?
So not myself. No, I don't really work with light myself. My own areas are in more so with structures, with respect to mechanical properties and the mechanics of motion and kinematics and that kind of stuff, robotics as well. So I don't actually work much with light at all whatsoever. But you know, all the points you made, I totally agree with. Anyway, it's just a case of that. Like I said, it's a 7-minute presentation. So but yeah. So for myself, you know, other people who would work with these structures are probably thinking in terms of thermoregulation, for example. That could be one area that's important to other people who work with these things. Also, Chris, in the last time I gave an example of this, Chris, who's on the NMA as well, he mentioned something about anti-fraud coloration for banknotes and that kind of stuff. So the people who work with this, you know, they will obviously have their own applications. Myself, I don't work with coloration.